Welcome to today's training session on the EPA 608 core section. This lesson focuses on the environmental impacts of refrigerants. We'll explore how the Earth's atmosphere and the ozone layer work, why chlorine and bromine are so destructive, and what that means for both human health and the environment. You'll also learn where most stratospheric chlorine really comes from, and how international agreements like the Montreal Protocol and the Kigali Amendment are addressing the problem. Finally, we'll walk through the major types of refrigerants, compare their ODP and GWP values, look at the phase-out timeline, and finish with essential best practices every technician needs to follow. Let's start with the atmosphere. The Earth's atmosphere has several layers, but the two that matter most for ozone are the troposphere and the stratosphere. The troposphere is the layer closest to the surface. At the equator, it reaches about 9 miles, or 15 kilometers, high. This is where our weather takes place. Above that is the stratosphere, which extends up to 30 miles, or about 48 kilometers. This is where about 90% of the Earth's ozone is found. Ozone, or O3, is a fragile gas made of 3 oxygen atoms. It forms a protective shield in the stratosphere that blocks harmful ultraviolet B rays from the sun. Now let's look at ozone chemistry. Ozone is unstable and can be broken apart when it comes in contact with chlorine or bromine. Chlorofluorocarbons, or CFCs, and hydrochlorofluorocarbons, or HCFCs, are very stable in the lower atmosphere. Because they don't dissolve in water, they can drift all the way up into the stratosphere. Once there, ultraviolet radiation breaks them apart, releasing chlorine atoms. Here's where the catalytic cycle begins. One chlorine atom reacts with ozone, creating chlorine monoxide and oxygen. Then chlorine monoxide reacts with another oxygen atom, regenerating chlorine and releasing more oxygen. This regenerated chlorine atom goes right back into the cycle. As a result, a single chlorine atom can destroy up to 100,000 ozone molecules. This was proven by the Rowland-Molina theory. And remember, bromine, which is found in halons, is even more destructive than chlorine. So, what happens when the ozone layer thins? For humans, it means more exposure to UVB radiation. That increases the risk of skin cancer, eye cataracts, and it can also weaken the immune system. For the environment, the impacts include damage to aquatic life, especially tiny organisms like phytoplankton at the base of the food chain. Crop yields can decrease, and materials like rubber, plastics, and wood break down more quickly in sunlight. The key point is simple. As ozone decreases, UVB levels rise, and that's why controlling refrigerants is so important for public health. Next, let's talk about where this chlorine comes from. Some people think volcanoes are the main source, but that's not true. While volcanoes do release hydrogen chloride, most of it doesn't make it into the stratosphere. In fact, studies show that about 82% of stratospheric chlorine comes from man-made chemicals like CFCs, HCFCs, and halons. Only 15% comes from natural methyl chloride, and just 3% from natural hydrogen chloride. Even air samples from volcanic eruptions show very little chlorine reaching the upper atmosphere. Now, how has the world responded? In 1987, the Montreal Protocol was signed by the United States and 22 other countries. This was a global agreement to phase out CFCs, HCFCs, and halons. Since then, monitoring has confirmed the presence of chlorine monoxide in the stratosphere, proving the science was correct. Later, the Kigali Amendment expanded the agreement to phase down HFCs as well. Even though HFCs do not harm the ozone layer, many of them have very high global warming potential. Let's shift to refrigerant types and their characteristics. CFCs, or chlorofluorocarbons, contain chlorine, fluorine, and carbon. They are extremely stable, with very high ODP and very high GWP. These are the most harmful to the ozone layer. Examples include R11 and R12. HCFCs, or hydrochlorofluorocarbons, contain hydrogen, chlorine, fluorine, and carbon. Because they are less stable, their ozone depletion potential is lower, but they still damage the ozone layer. R22 and R123 are common examples. HFCS, hydrofluorocarbons, contain hydrogen, fluorine, and carbon, but no chlorine. That means zero ozone depletion potential. However, many HFCS have very high global warming potential. Examples are R134A and R410A. HFOS, hydrofluoroolefins, are similar to HFCS, but they're more chemically reactive. They have zero ODP and very low GWP. Some, like R1234YF, are mildly flammable, but they're becoming widely used in automotive systems and chillers. HCS, hydrocarbons, are natural refrigerants such as propane and isobutane. They have zero ozone depletion potential and very low global warming potential, less than 4. However, they are highly flammable, so safety precautions are critical. HFES, hydrofluoroethers, contain hydrogen, fluorine, carbon, and oxygen. They have zero ODP, but their GWP values vary widely. They are not commonly used as primary refrigerants. Now let's compare ODP and GWP. Ozone depletion potential, or ODP, measures how much a refrigerant can harm the ozone layer. The reference standard is R11, which has an ODP of 1. Global warming potential, or GWP, measures how much heat a refrigerant traps in the atmosphere over 100 years. The reference standard is carbon dioxide, which has a GWP of 1. Here are some examples. R12, ACFC, has an ODP of 0.82 and a GWP of 10,600. R410A, an HFC, has zero ODP but a GWP of about 3,000. R-1234YF, an HFO, has zero ODP and a GWP of less than 1. Let's also look at phase-out regulations and the transition timeline. CFCs have been completely phased out worldwide. HCFCs are banned in new systems, and after 2020, only reclaimed HCFCs may be used. HFCs are being phased down under the Kigali Amendment because of their high GWP. HFOS and hydrocarbons are encouraged as replacements, but they must be handled with safety in mind. 2 important rules to remember. The pre-charged appliance rule. This prohibits selling new systems pre-filled with HCFC 22 after 2010. And the allocation rule. This bans the use of virgin HCFC 22 in new equipment. Finally, let's review technician best practices. Always recover refrigerants that have an ODP greater than 0 or a GWP greater than 1. Never vent refrigerants. It's illegal and damaging to the environment. Clearly label systems that use flammable refrigerants, such as hydrocarbons or HFOS. Check system compatibility before retrofitting, and use the correct lubricants. For example, HFOS requires synthetic POE oils. And remember, hydrocarbon systems like R600A must use extremely small charge sizes and must be clearly labeled due to flammability risks. Okay, to sum it up, the ozone layer protects us from UV radiation. Chlorine and bromine destroy ozone through catalytic cycles. Ozone depletion has serious effects on human health, the environment, and materials. Most chlorine in the stratosphere comes from human-made chemicals, not volcanoes. The Montreal Protocol and Kigali Amendment are global agreements leading the transition to safer refrigerants. And technicians must follow recovery, safety, and labeling best practices to protect both the environment and themselves. If you're preparing for the EPA 608 exam, review these refrigerant categories, ODP and GWP values, and phase-out rules carefully. Check out the next lesson for practice questions, and don't forget to subscribe so you can keep learning with us.